Throughout the 20th century, a number of discoveries revolutionized our universe. The discovery of the interior structure of atoms as well as radioactivity led to the quantum revolution, exposing the bizarre and counterintuitive rules that nature plays by at a fundamental level. The birth and growth of experimental particle physics led to enormous theoretical developments, enabling everything we observe to be represented as composites of indivisible quanta. At last, in the late 1960s, the final theoretical pieces of our quantum universe were put into place, completing what we know today as the Standard Model. More than half a century later, every prediction it's ever made has been borne out by experiments, with no conflicts at all. Arguably the single most important person in completing the theoretical development of the Standard Model of elementary particles was Steven Weinberg. On July 23, 2021, he passed away at the age of 88, leaving behind a rich legacy of accomplishments spanning a wide array of topics in theoretical physics. Although he may have left this world, his contributions are destined to vastly outlive him, as they're now central to not only physics itself, but have been highly influential and educational to generations of physicists. Even though the Standard Model is now an orphan theory, having outlasted its primary architects, its reign as the most successful theory in the history of science continues, and so shall the legacy of Weinberg's contributions to the field. Even to physicists and physics students who never got the opportunity to know him personally, his lasting influence has been nothing short of titanic. A Model of Leptons. In 1967, Weinberg submitted an under 3-page paper that, for the first time, correctly surmised the particle structure of electroweak unification. The big issue at the time was that any broken symmetry inevitably results in the generation of at least one massless gauge boson, known as a Goldstone boson. But in order to explain radioactive decays, as well as the other effects of the weak force, a massive set of spin-1 bosons needed to exist. This was the problem that Weinberg set out to address in his paper, simply titled, A Model of Leptons. Weinberg began by hypothesizing an unbroken, unified, more symmetric state that appears at high energies, then breaks at some lower energy scale to produce the weak and electromagnetic forces we see today. What Weinberg showed was that if the photon and the intermediate-boson fields serve as the gauge fields, which they do in the case of the Higgs mechanism, then that broken symmetry can lead to, although many others made very important contributions to the puzzle, Weinberg was the first to put the theoretical pieces together to create what we know today as the Standard Model. In all the particle physics experiments that have come since, not a single one has disagreed with its predictions. Weinberg's mechanism was not only prescient, but correct.